We are going over the final exam from fall 2019, Calculus 1, and we begin with an average rate of change and instantaneous rate of change problem. The first part, average rate of change on the interval 1 to 3, this would be f of 3 minus f of 1. This is the change in f divided by 3 minus 1, which is the change in x. Now we can come to the side, calculate f of 3. This is 2 divided by, would be the square root of 12 minus 3. This is the square root of 9. F of 3 is 2/3. Similarly, f of 1 is 2 over the square root of 4 minus 3, which is 1. F of 1 is 2. So here, this is 2/3 minus 2 divided by, well, 3 minus 1 is 2. So this is 2/3 minus 6/3 times a half. This is negative 4/3 times a half. This is negative 2 over 3. So this is the answer here for part A. Now for part B. This is the exciting part. Definition of derivative. Well, we want the derivative at 1. So this will be a limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. What I will do is I will start with the numerator of this difference quotient, and I will simplify until I get h times something, and then I can divide by h. Well, this is 2 divided by square root. We have 4, 1 plus h minus 3, and then minus, we have 2, the square root. Well, in fact, we've already calculated f of 1, so maybe I will just write that. We can use above here, that f of 1 is 2. So this is 2 divided by the square root. We have 4 minus 3, which is 1, and then we have plus 4h. So 4h plus 1. Now, what I will do is get a common denominator, which is, we see, square root 4h plus 1. So I will go ahead and multiply this 2 by this common denominator of square root 4h plus 1 divided by square root 4h plus 1. Now you see I can add. I have one fraction and it has this common denominator. I have 2 minus 2 square root 4h plus 1, and then divided by this square root 4h plus 1. Well, what's our strategy now? I still don't have h times something. Now what we do is what we do if we have just the derivative of, using the definition of, say, square root of something. The trick in that case is you want to rationalize the numerator, and this is what I will do now. So I will multiply here by, well, it will be 2 plus 2 times the square root 4h plus 1. And you also multiply this in the denominator. What happens when I do this? Well, the reason I did this is because first and last is all I have. You notice if you multiply the inner and the outer, these add to 0. I'm left with, when I multiply the firsts, I get 4. When I multiply the last, I get minus 4. And then I have this 4h plus 1. And it might not look like I've made this any simpler. Oh, well, my denominator is definitely not simpler. My denominator has more things, but this is perfectly fine. The numerator is what I'm trying to make simpler. And you notice it is. So we have 4 minus 4, which is 0, and then we have minus 16h over this denominator here, which this part I'll just recopy. Now you see I have this as h times something. So when I go to take a limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h, this is a limit as h approaches 0. It's just minus 16 over this denominator. And this, we can just evaluate h equals 0. This is the beauty of the simplification that we did. This is minus 16 over. Well, what happens when you substitute h equals 0? We get the square root of 1. Oh, we just get 2 plus 2. Square root of 1 times 2 plus 2. So this is, I have minus 4. Now, this is fine. We are finished with the problem. But if you want to, you can check. Maybe I will. When I check, well, the original function was 2 times 4x minus 3 to the minus 1/2 power. And this would be minus 1, 4x minus 3 to the minus 3/2 power, and then multiply by the derivative of the inside function here. Well, at x equals 1, which is where we calculated this, we get, this part here is just 1 to a power, which is 1, this part. So we have minus 1 times 4. We get minus 4. My work in green checking, this is optional, and this is not worth any points, not when you're using a definition of derivative to calculate. The last part is equation of the tangent line. Well, we know a point would be 1 comma f of 1, and the slope is the derivative at 1. We calculated, this is minus 4, and we also calculated f of 1. That was, in fact, one of the very first things we did, all the way up here at the top. F of 1 is 2. And so this would be, for instance, y minus 2 is minus 4, x minus 1. This would be an equation of this tangent line. Okay, now we have a polynomial. We want to know lots of things: critical points, increasing, decreasing, local max and min. We will have global max and min and concave up and down all in one problem. Okay, the first thing we need to take the derivative. And critical points by definition are where the derivative is 0 or does not exist. They are x values in the domain. So this is 4x cubed minus 12x squared. I can factor out 4 and x squared. I'm left with x minus 3. So the derivative equals 0. Well, this happens when x is 0 and 3. Okay. Now, we want increasing, decreasing. And the way I always do this, I make a number line and I subdivide based on my critical points. And this lands us into 3 open intervals. We take the domain of the function, subdivide into open intervals based on the critical points. And my open intervals are minus infinity to 0, 0 to 3, and 3 to infinity. Then we want to test the derivative. And my derivative is here. Okay, and I will use, let's see, I can use minus 1, I can use 1, and I can use 4. For example, these are not my only choices. So we want minus 1, 1, and 4. Now, 4x squared is always positive. So we have plus, plus, and plus. Here, x minus 3 is negative, negative, and positive. So you see my derivative. My derivative is negative, negative, and positive on these open intervals. Therefore, the function is increasing. Well, this happens everywhere we see a plus, which is 3 to infinity. And it's decreasing everywhere we see a minus. Now, you can either write like this, just list the intervals with a comma. That's what I'm going to do. In this case, because the intervals meet here at 0, you could combine them into 1 and write minus infinity all the way to 3. But it's perfectly fine just like this, increasing and decreasing. Now, we want to classify critical points as corresponding to local max, local min, and or neither. So x equals 0 and x equals 3. Well, you could use second derivative test, for example, but I'm going to use what we've done. We've done all the work. All of the work is here for the first derivative test, really. So what do we have here? At 0, look, we are decreasing, decreasing, right? Okay, decreasing, you could put a horizontal tangent, but decreasing again. And so this is neither. And at x equals 3, well, we are decreasing and then increasing. X equals 3, this is a local min. Now we move on. We want the absolute. These are global extrema. It does not matter for global extrema if you are decreasing and then increasing, or if you were increasing, decreasing. The only thing that matters, we want the highest overall y value, global max. Lowest overall y value, global min. And this is what we are trying to do now. Okay, we are on a closed interval, which means extreme value theorem. We are guaranteed to have both a global max and global min. Now, how do we find them? Well, again, I make a little chart like this, where we put the critical points, but it's not the derivative this time. We want the original function to the 4th minus 4x cubed plus 1. And we put our critical points, but we also must add the endpoints. When you're on a closed interval, the endpoints are critical points. Now, one of them we already had above, but now we have all of the critical points on our closed interval. And at this point, you just evaluate the function. Okay, we can see this is 1. Then, if you use your calculator, the function at 3 is minus 26, and the function at 4 is 1. Okay. We look at this, and we just pick the highest overall y value. That becomes our absolute max. So we have an absolute max of, well, we have 2 places where this occurs. We have 1 absolute max. I should say 1. Y equals 1. But it happens at 2 x values. It happens at 0 and 4. And then we have an absolute min of y equals minus 26. And this happens at x equals 3. This is part D. Now the last one is about concavity. Let me copy the derivative, because concavity, this has to do with second derivative. And in order to get the second derivative, well, of course, we take the first derivative and then we differentiate. The second derivative is 12x squared minus 24x. And again, I can factor out what's common to both, which is 12x and x minus 2. You see the second derivative is 0. Well, this happens when x is 0 or when x is 2. It does not mean necessarily that these are inflection points. Let's see, open intervals. This doesn't ask inflection points, but certainly once we answer the question, we could answer what are the inflection points. Okay, well now I subdivide like this. I have these three open intervals, here, here, and here, and I want to test. This time, these are intervals, I'm looking at concavity, and so that means I test the second derivative. This is what tells me about concavity. Well, I see the second derivative here. It's 12x times x minus 2. I will test at minus 1, 1, and 3. And 12x, let's see, this is negative, positive, positive. X minus 2, negative, negative, positive. And so you see, I have, for the second derivative, we have positive on this interval, negative on this interval, and then positive on this interval. This is concave up. Everywhere we see a plus, which is minus infinity to 0, and 2 to infinity. And then concave down, there's only one interval here. This is 0 to 2. And this completes this problem, multiple parts. In fact, as a comment, as I mentioned earlier, here, 0 and 2 are both inflection points because at 0 it's concave up on this side, concave down on the other, and at 2 it's concave down on this side, concave up on the other. Number 3, we have a parameterized curve. This sits, you see we have 3 components. This is in R3. Part A, we want the velocity at time t equals 0. Well, the first thing we need to do is just calculate the velocity as a function of time. And how do you differentiate something like this? Well, we differentiate each component. The first component is a square root. This would be 1/2. Well, it would be t plus 1 to the minus 1/2, which is 1 over 2. Square root t plus 1. Derivative of the inside function is just 1. Now you differentiate 2 sine, we get 2 cosine t, and differentiate 2 cosine, we get minus 2 sine. This is the velocity as a function. Now we want to evaluate at 0. At 0, we have 1/2. The cosine of 0 is 1, and the sine of 0 is 0. So this is our answer for part A. The velocity at time t equals 0. Now part B, we actually have 2 parts. We want the speed, and then we want the time at which the speed is 3. Now, this is the one, this will be weird. I'm just telling you in advance. We will get a negative time here. And this may not have so much of a physical application. So I will just tell you this in advance. We'll get a negative time. But here we go, speed. The speed is the length of velocity. I can put hats, maybe I will. This is a square root. Now, you take each component and square, but you need this as a function of t. So when I square the first component, this is 1 over, this would be 4t plus 4, right? Because squaring this gives us t plus 1. So we have t plus 1 in the denominator times this squared, which is 4. In fact, this is exactly what we see here. Then I have 4 cosine squared, and then plus 4 sine squared. Now, sine squared plus cosine squared is 1. And so 4 cosine squared plus 4 sine squared is 4. So we get the following for the speed. This is fine to leave as the final answer for the speed, but because I will be solving when is the speed equal to 3, I'm going to get a common denominator. This would be 1 plus, this would be 16t plus 16 all over 4t plus 4. Maybe I'll leave it like this on this line. So this is fine. Either one of these, maybe I'll underline this one as my formula for speed, but it's also equal to this right here. Now, let's do the second part. We want to set this equal to 3. When I do, my numerator, I have 16t plus 17. And in the denominator, I have 4t plus 4. What I can do is just square both sides. And I get that 9 is 16t plus 17 divided by 4t plus 4. Now, how do we solve something like this? We can just multiply through by the denominator, which is 4t plus 4. And when I do, I get 36t plus 36 equals 16t plus 17. If I subtract, I have 20t on this side, and then subtract 36 from both sides. On the other side, we have minus 19. And this is what I was saying. Our final answer may not have that much of a physical interpretation, but we have solved the problem, which is that t is minus 19 over 20. Okay, now this is the last part of this problem. We want the acceleration at time t equals 0. To get acceleration, we take velocity and then we differentiate. Now, maybe I should come to the side and do some side work just for this one component. You notice the first component of velocity is the following. It's 1/2 t plus 1 to the minus 1/2. And when I differentiate this, I get minus 1/4 t plus 1. Now, power minus 1, this is minus 3/2. Okay, then times derivative of the inside function, which would give me times 1. So here, the first component of acceleration is exactly this. It's minus 1/4 t plus 1 to the minus 3/2. And then we just differentiate to cosine, we get minus 2 sine. And we differentiate minus 2 sine, and we get minus 2 cosine. This is acceleration as a function of time. Now, what do we need? We need the acceleration at 0. You see here, evaluate this as 0. We get 1 to the minus 3/2, which is just 1. So this is minus 1/4. And then the sine of 0 is 0. Cosine of 0 is 1. So this is the answer for part C. Okay, this is the end of this particular parameterized curve problem. Now for number 4, we try to evaluate. This is a limit as x approaches 0 of this function. We would have 0 over, well, cosine 0 is 1. So in fact, we get 0 over 0. This is our signal to do something, in particular, L'Hopital. So this equals, using L'Hopital, well, we will take the derivative on the top, take the derivative on the bottom, reevaluate the limit. And when we do, we get 6x divided by, well, the derivative of cosine is minus sine. We have a minus in front. So this would just be sine of x. What happens now? Do the same thing. Try to evaluate. We get 0 over sine of 0 is 0. Okay, we have 0 over 0 again. This here is always your signal when you're using a limit or trying to evaluate a limit. to do something. And in this case, we can use L'Hopital again. So this, we have to do L'Hopital a second time in this example. Sometimes this happens. Take the derivative on the top, take the derivative on the bottom, and reevaluate the limit. Now you notice we get 6. Cosine of 0 is 1. So this limit is 6. This limit exists and equals 6. Number 5, here we have many rules for derivatives. You notice I see a product. First of all, we do not want to simplify. Every time we simplify, it introduces the possibility of error, and that's not the goal. You see this here. The goal is to just differentiate, and we will use many rules. So in the first one, part A, the first rule I see is a product. I might write this in 2 steps. When we go to take the derivative, well, this would be first, which is x to the 2/3 plus 1, and then times the derivative of the second, which is here, x squared e to the x plus 3, and then plus, well, the second times, well, the derivative of the first, this I will just do, 2/3 x to the minus 1/3. That was power rule. The derivative of this 1 here is 0. Now, well, I have, this is the derivative, except I have this one piece left still to calculate. So I recopy. Okay. Well, it's chain rule followed by product rule. So when I go to differentiate this part, you see here is my first inside function. I can do this. Derivative of natural log is 1 over x, but I have this inside function, which is x squared e to the x plus 3. Then multiply by the derivative of the inside function. This is a product. First derivative of the second plus the second times derivative of the first. Okay. So this, which is in these brackets here, is exactly the derivative of this function. Then I can just recopy. You see, I've already differentiated this part. This was the other part of my original product rule. So altogether, this is my final answer. I am not simplifying this. Now for B, fundamentally, you see, looking at B, I see one function divided by another function. So the first thing I'm going to do here is quotient rule. But then, of course, I will also have some chain rule when I go to differentiate the numerator and differentiate the denominator. Okay, quotient rule, v prime of t. This equals, we have denominator times the derivative of the numerator. Derivative of 1 is 0. The derivative here of sine e to the t, this in itself is a chain rule where the inside function is e to the t. So we have minus cosine e to the t times e to the t. So far, this is first, this is denominator, derivative of the numerator, then minus numerator, derivative of the denominator, which is minus sine 2t times 2. And then all over denominator squared. So this is cosine of 2t squared. This is my answer here, final answer. Finally here, we have some inverse trig functions. Wonderful. We want, this is a sum of 2 terms. That's what I see first. It's a sum of 2 terms. Each term is a chain rule. So the first thing, we differentiate the sine inverse, which would be like this. There's a square root, and then 1 minus squared. Right? This is the derivative of sine inverse. Then I put in the entire inside function, which is square root of y. Then multiply by the derivative of the inside function, which is here. Okay, this is the derivative of the first term. Now, of course, you can simplify this sum. The square root of y squared is just y, but I will leave it like this. Then we have minus. Okay, what's the derivative of tan inverse? It's 1 over, like this. We put in the entire inside function, which is 5y plus 1. And then the final part of this one is multiply by the derivative of the inside function, which here is 5. Okay, so this is my final answer here, unsimplified, but that's certainly how I would leave it. Number 6, logarithmic differentiation. This is a great problem to practice. What can we use if you have a product on the inside? This is a sum. If you have a quotient on the inside, this is a difference. And finally, if you have a power on the inside, this is b ln of a. I'll put parentheses. Okay, these are the properties of logs that we use when we use logarithmic differentiation. Sometimes, maybe I'll write this, I won't use it in this example, just looking at the function, but we can also use that ln of, let's say, e to a power is just this power. So you will also see that, not in this problem, but sometimes you'll see that. So let me call this y. This is the way I always think about it. This is y. And then we are ready to begin logarithmic differentiation. What we want to do is take the natural log of both sides. So ln of y will be equal to ln of x to the 2x cosine x divided by, we have the square root of x cubed plus 1. Now, we need to use these pink properties to simplify the right-hand side. So this is ln of, we have x to the 2x cosine x. The first one I'm using is the difference. So minus ln of, this is a square root of x cubed plus 1. Okay. Now, I can keep going, and I absolutely should. Here, this first one is a product. I can write this as a sum. Now, maybe I'll just rewrite this, but I will rewrite it as a power. This is x cubed plus 1, and then square root is a 1/2 power. Now I can take one more step to simplify. And this term alone is really what makes logarithmic differentiation so powerful. Function raised to a function. So this is 2x ln x. And then this I just recopy. And the final thing I can do here is I have a power. So this is 1/2 ln of x cubed plus 1. And now this is as simple as I can make this. Okay? Now remember, none of this is derivatives. This is still ln y. Now is when I'm ready to start differentiating. The left-hand side is 1 over y, y prime. This was really a chain rule. Now I just differentiate every term on the right-hand side. We have first times derivative of the second, and then plus the second times derivative of the first. Now, when I differentiate ln cosine of x, this is chain rule. We have 1 over cosine, and then times derivative of cosine is minus sine. Finally, this third term, we have the minus 1/2, but then this is chain rule, where we take 1 over x cubed plus 1 times 3x squared. Okay? Maybe I should put parentheses here. Now, the final step in logarithmic differentiation, we multiply through by y, but we want to write this as a function of x. So let me just copy it from here. Here is y as a function of x. I can just recopy everything I see. This is 2, and then plus 2 ln x. This is in fact, sine over cosine is in fact the tangent. And then we have minus, up here we have a 3x squared, and in the denominator, this is 2x cubed plus 2. Okay, so this is my final answer here. This was logarithmic differentiation. Okay, we have inverse function theorem. The first thing we want is, what is f inverse of pi cubed? Well, you just kind of have to guess and check, but it's not going to be anything too terribly hard. For instance, it's not going to be 462 because that would be really hard to guess. And we are not trying to solve x as a function of y. That is not the goal. We want to use the inverse function theorem. So you notice we have this trig function, sine of x plus x cubed. And if we just evaluate, so I will make this comment, notice f of pi is, well, it's sine of pi plus pi cubed. And sine of pi is 0. So we get pi cubed. Immediately, this tells us the answer to part A. This tells us that f inverse of pi cubed is pi. This is this inverse relationship. If f of pi is pi cubed, f inverse of pi cubed is pi. Okay, great. Now, part 2. Letter B. We want to find f inverse prime at pi cubed. Well, inverse function theorem says this is 1 over f prime of f inverse of pi cubed, which is 1 over. Now, we found f inverse of pi cubed in part A. So this is 1 over f prime of pi. Okay? This is what you should put stars around. This is inverse function theorem. This is what we use in whenever a problem asks for the derivative of an inverse. We do not solve x as a function of y here. Okay, great. Now, what do we need to do? Calculate the derivative of f. Evaluate at pi. That's this. And then take 1 over. So the derivative, well, we can certainly differentiate this function. Derivative of sine is cosine. Derivative of x cubed is 3x squared. And the derivative at pi is, well, the cosine of pi is minus 1. And then here we get 3 pi squared. So now I'm ready for my final answer. This is 1 over, we have minus 1 plus 3 pi squared. This is my answer here. Okay, inverse function theorem. Number 8, this is optimization. Here is an open box. It's supposed to be, this is supposed to have a square base. So let me start labeling. This is x, and this is x, and then we have some height y. And we're given the volume. Okay, what is the volume? This is one reason we label things. The volume is x squared y, and this is supposed to be 27. This, you see, this is an equation, and therefore it is my constraint equation. Now, we have cost, and if we read the question, we want to minimize the cost. So what is the cost? Well, here's where we have to look also at our graph and understand there is no top. The cost, the bottom is $15 per square foot, and the bottom is x squared, the area. And the sides is $7.50 per square foot. We have 4 sides. They are here, x by y, x by y, x by y, and x by y. Altogether, the area of the sides is 4xy. So we would have this times 4xy. This is the cost. You see, this is a function we are told we want to minimize. Therefore, this is the objective function for our optimization problem. Now, what do we do in optimization? The first thing we want to do is use the constraint to solve for one variable in terms of the other. In this case, it's much easier to solve y as a function of x because we don't have to take a square root. So y is 27 over x squared. This was my initial step right here. Okay? Then we use this. This will allow me to get cost as a function of one variable. We love function of one variable because this is calculus 1. Okay, so we have 15x squared plus, well, 4 times 7.5 is 30. And then we have x. Then we have 27. I'll write it this way, x to the minus 2. Which I can write as 15x squared plus, let's see, this would be 810 x to the minus 1. And the domain here, if you want to think about this, well, x and y both have to be positive. So in particular, I can do this. No matter how large x is, well, I could find some y that's positive with this relationship. So the domain is 0 to infinity, and we want to minimize. And an important part of this is to check that you have a minimum, as we will see. Now, how do we minimize a function in Calc 1? We take the derivative. We set it equal to 0. We look for critical points. The derivative here is 30x minus 810 x to the minus 2. When we set this equal to 0, we get 30x is 810 over x squared. Now, from here, what do we see? Well, we see that we must have 30x cubed is 810, or that x cubed is 27. And this means that x is 3. We have exactly one critical point. Now, it is not the end because remember, we must actually check that x equals 3 corresponds to a minimum. And then we need to go back and read the question and see what are we reporting back here. So to check that you have a minimum, you can either use, because this is an open interval with just one critical point, you can either use first derivative test or second derivative test. Maybe I'll use second derivative test. This function is not too terribly hard to take the derivative again. It's all power rule. So this is 30 plus 2 times 810 x to the minus 3. You notice on the entire interval 0 to infinity, this is positive. But in particular, at 3, this is positive. This says here, concave up. This says, in fact, we have a min at x equals 3, which is what we're looking for. Very nice. The final part of this problem is to go back always. The last part of a optimization problem is go back, read the question, and you notice we are asked here, dimensions of the box. The dimensions, well, we have 3 of them. This is x by y, and we use this relationship that y is 27 over x squared. Y is also 3. So my final answer is here. Now for my favorite part of the semester, which is integration. If we look at this function, you see there are parentheses here. We have an inside function, and we have a multiple of its derivative in the integrand. This is substitution, where u is the square root of x, and then du, well, we differentiate. This is 1 over 2 square root x dx. Now, we have handed to us in our integral just 1 over square root x dx. And this is 2 du. This is my work for substitution. This is, we have sine of u times 2 du. Now, when we integrate sine, negative cosine, So this is minus 2 cosine u plus c. And the final step, go back to x, minus 2 cosine of the square root of x plus c. This is our final answer. Now for b, we see parentheses, inside the parentheses the natural log, and we see a multiple of its derivative. So u is ln x du, this is 1 over x dx, and we have exactly du in our integral. Now, this is definite, which means I will change my bounds. X goes between 1 and e cubed. When x is 1, u is the natural log of 1, which is 0. And when x is e cubed, u is the natural log of e cubed, which is 3. With a definite integral, you have some choice. You can either, as I always do, change your bounds. So this would be u ranges between 0 and 3, and then I have u squared du. This is one option. As I was just saying, you can change your bounds to be u bounds. The other option is to first find a capital F of x, which is an indefinite integral. Then evaluate at the x limits of integration and take the difference. But that's not the way I do it. I find it a lot easier to convert to an entire integral of u. Then I evaluate at a u upper limit of integration, a u lower limit of integration, and take the difference. So this is, it's u cubed over 3, evaluated between 0 and 3. This is 27 over 3 minus 0. So we just get 9. This is our answer here. Now there's one more integral on this page. This is not substitution. This is, well, we write this as a sum. We have 3x over x squared. We have plus the square root of x over x squared. Now the first term, properties of exponents, is 3 over x. And the second term, I will write this as a power. We have a 1/2 in the numerator. We have a 2 in the denominator. Altogether, this is a minus 3/2 power. Maybe I should write that as part of my side work. This is minus 3 over 2. So the second term, as I was just saying, this is x to the minus 3 over 2. And then I have dx. When we integrate 3 over x, this is not a power rule. This is 3 ln absolute value of x. And then here, the second term is a power rule. We add a power, divide by the higher power. And I personally would probably just put it here. You can leave this as minus 1/2 power. You could also write this negative x to the minus 1/2 as a square root in the denominator, but I will leave it like this. Okay, so this is our answer for C. Number 10, this is a Riemann sum. The first thing we want to do is calculate delta x. You notice we want to write Riemann sum with 5 subintervals. So delta x is b minus a over n. This is always the way it is when we have equally spaced subintervals. This is 1/5. Now, step number 2, write down the partition. You start with the left endpoint. Let's see, I'm going to write these all as something over 5. So this is minus 10 over 5. Then we march forward by delta x until we hit the right endpoint. So this would be minus 9 over 5, minus 8 over 5, minus 7 over 5, minus 6 over 5, and then finally minus 5 over 5. That is minus 1. That is our other endpoint. So this is the partition I will use. Now, one more piece that's important is this. We want a right Riemann sum, which means we use the right endpoints. In my sum, I will use this, 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 and this. Okay? Now, one more thing I will do before I get started. It might help me to write the function slightly differently. So my function is the square root of its x plus, well, 2 is 10 over 5. You see, this will help me when I write out everything. Now, what is the Riemann sum? Well, if we write it in summation notation, this is what we want. It would be I goes from 1 to 5. The right endpoint is f of xi, and then delta x. But my delta x is 1/5. I can factor out and write the delta x like this, and then I will just have a sum of the function evaluated at these right points, which are underlined in pink. So when I evaluate the first one, well, maybe I'll write all the square roots. This would be 2, 3, 4, and 5. We have minus 9/5 plus 10/5. This is 1/5. Minus 8/5 plus 10/5. Minus 7/5 plus 10/5. Minus 6/5 plus 10/5. And finally, minus 5/5 plus 10/5. The second part is evaluate. Okay, well, at this point, you put this whole big line into your calculator or Desmos, something like this, and we can figure out what this is. When I do, I get this is approximately 0.7497. So this is the answer for B. This is B, and this is A. This is area between two curves on this region, -1 to 2. And my picture is not accurate. It's just a basic sketch where we see how to set up the integral. Now, how would you actually find -1, 0, and 1? Well, we set the two curves equal. And this gives us, say, x minus x cubed is 0. We can then factor. This is x, it's 1 minus x, and 1 plus x is 0. Okay, and you see, here's where we can get these points. We can also see it just by graphing, and by graphing in Desmos, say, we would have a much better picture than I have sketched here. But what do we see from my picture? We see exactly how to set up this problem. We break this into a sum of 3 integrals, in fact. We will integrate -1 to 0 of upper minus lower. We integrate 0 to 1 of upper minus lower. And then we integrate 1 to 2 of upper minus lower. Okay? Now, in this particular problem, there is symmetry here. So this area and this area, in the picture, it is here and here. It may not look it, but it is the same. We have symmetry. So it can save us just a little bit of work to do this. Take 2 times the integral 0 to 1 of this. This would give us the total area. I have shaded in pink. And then we have this part, which I don't have shaded. I don't even have this function going far enough to shade. I did it just far enough to set up the right integral. Okay? This is what we want to calculate. Oh, you can't see the 3. Well, let's integrate. We get x squared over 2 minus x to the 4th over 4. Evaluated between 0 and 1, plus we have x to the 4th over 4 minus x squared over 2. And again, evaluated between 1 and 2. So let's, at this point, fundamental theorem of calculus, evaluate at 1. We get 1/2 minus 1/4. When we evaluate this at 0, we get 0. Maybe I won't write that. Then evaluate at 2. 2 to the 4th is 16. Evaluate at 2. Okay, then subtract. Evaluate at 1. This is 1/4 minus 1/2. We have 2 times a 4th, which is a half. We have plus 2, and then we have minus a 4th, which is plus a 4th. This is 2 3/4, otherwise known as 11 over 4. This is our final answer. Okay, 11 over 4. Now, this is the end of this final exam from fall 2019. I hope this was helpful. Thank you very much.